Hello, everyone. Can you hear me? All good? So there's a lot of things I want to cover today, so I'll get right into it. The first thing I want to just mention is that I'll share my screen and kind of show you. So the first thing I really want to talk about is today's session is introduction to machine learning. We're going to go as much as we possibly can into machine learning inside a 2-hour window. Having said that, we won't cover everything, but the idea is that we cover a little bit of how the theory meets the application. What I mean by that is we'll talk about basic machine learning principles, and then we'll actually do some code, and the code should be relatively easy to work with. And in the chat right now, in a comment, I have a link to the content for today. So please, if you haven't cloned already, please do. I've also updated the content just a little bit since, I don't know, 20 minutes ago, because I want to have more content in there just in case you have extra time. So with that, I'll give everyone about a minute to clone and follow along with me. What I'll do right now to make it a little bit easier for everyone to follow along is you can see on my desktop, I have the content for today's lecture. I'm just going to clone it onto my local machine. And if for some reason you can't follow along, please just, you can watch. If you can't follow code-wise, just look at my screen, see if you can understand the principles, because I really want you to understand the concepts more than just about anything. So what I'll do, because I know this is not a Git lecture, I'm going to clone it locally. So I got the link over here. I get clone. For those of you that aren't familiar with Git, you can literally do the same thing, or effectively the same thing. Download a zip file, and then once that's downloaded, you can unzip it. As you can see, I have quite a few things in here, but I'm going to use the one from my desktop. And throughout today's session, one thing I really want you to do is, if you find that I'm going too fast or you have a question, feel free to ask. I'd rather answer the questions while they're still in your mind and while they're pertinent, rather than waiting to the end of the session, because 2 hours is a long session and it might not be valuable for you if you wait till the end of the session. So this folder is called ML Model Scikit-learn. So I'm CDing into that repo. And then from there, we have a lot of content. The one thing I want to mention here is this is more content we can probably cover in one session. I just have extra content in case you find that you want to learn more, you want to go further. And of course, feel free to add me on LinkedIn, add each other on LinkedIn for one, share your LinkedIns with each other. It's probably a good idea. So we'll go through quite a few things. The first thing we'll do is we'll have an introduction. So this is what I'll go over right now. So I'm not going to spoil the slides, so to speak. Basically, what is machine learning? Why do we care? And then why are we using Scikit-learn to do machine learning for this 2-hour session? From there, I have some tools I recommend if you want to set up a computing environment. If you want to run things locally, you can do it through Anaconda or similar, or you can use Google Colab if you want a free online version. The stuff we're running today is not that computationally intensive, but you still might want more compute eventually. So Google Colab is a little bit limited. From there, we'll talk about how to format data for machine learning. Like, why is it important to get data in a certain format to then put into an algorithm? From there, we'll go into something that most of you probably already will know with linear regression. The point of that notebook will be essentially to talk about to basically get you familiar with the syntax of code, not necessarily the concepts. Because in machine learning, you can have a couple of types of errors. You can have an error that is syntax related, and you can also have an error that's conceptual. So I want you to have less errors in the syntax end. So we'll start off with linear regression. And then we'll talk about things like why you split your data into training and testing sets. We'll go over decision trees, how to visualize them. We'll talk about random forests, as well as some other statistical concepts that go along with those. And then from there, we'll go over logistic regression in way too much detail, to the point where you might be questioning why I'm going over that so much. Throughout this process, we'll really try to connect the theory to the application. So with that, I'll get out my slides and I'll give a quick presentation before we get into understanding the theory through code. So about me, I'm a machine learning PhD student at the Georgia Institute of Technology. And as far as my background, I used to work on understanding like wearable data, so long-term trends in sleep, heart rate, and activity. And before that, even during that, I worked as a machine learning instructor at Stanford Continuing Studies, UCSD Extension. I've had LinkedIn Learning courses for years now. I also, these days, as a grad student in ITA, I previously worked at Anyscale, Intel, and a couple other places. And so I'm very passionate about this data science and machine learning landscape. As far as what you should know for this talk, of course, it's nice if you know linear regression, if you've seen it. If you've been in Excel and you see nice linear lines, I'm pretty sure most people have seen it, but if not, no worry. Ideally, it's nice if you're familiar with some basics about Python strings, integers, floats, tuples, for loops, lists, dictionaries, whatever. It's just nice to be able to not have to worry about that end of things as we kind of get into the theory and the application of machine learning. Having said that, if you're not familiar, I'm happy to share resources like after this talk, so to speak. As far as what machine learning is, one way that Arthur Samuel first coined it is the field of study that gives computers the ability to learn from data without being explicitly programmed. The part about not being explicitly programmed is really before machine learning, we've tried to find ways to extract information from data without giving essentially a lot of conditionals that are hand-coded, so to speak. As far as the actual learning part of machine learning, it's really when we give these models tunable parameters. We call these hyperparameters, and we'll talk about that throughout all the models we cover today, that can be adapted to observe data. So in theory, the program can be considered to be learning from the data. This is a quote from Jake Vanderplas. He's been around for a long time. I think he did the Python Data Science Handbook back in the day. It's still fantastic. And I reckon you check it out. So, and then once the goal of machine learning, of course, is it's not just about having models that do well at predicting from previously seen data, as we'll see today. It's about seeing if they can be used to predict and understand aspects of newly observed data. This is why we're going to talk about the train test split, so to speak, and cross-validation. So we don't just have models that memorize or train data, but also do well on data it hasn't seen before. That's a really, really important thing we'll talk about today. As far as two very basic types of machine learning, one of them is supervised learning. And this is essentially when we have a feature and a target. So if we're looking at things like home prices, for example, and you want to predict home prices based on some features, like i.e. columns of data, like number of bedrooms, bathrooms, square footage, is it by the water or not? Those are features. And the thing we want to predict often is a target. For supervised learning, if it's a continuous thing, like price of a house, that can vary between a couple 100,000 to a couple million, if not even more in some cases, well, that's a continuous thing. We can also predict something that is essentially a class. So is this a can? So I'm drinking a Waterloo during the speech. It's not sponsored by that. Or is it a phone? These are two classes. Predict whether it's one thing or another. That's a binary classification problem. And as far as unsupervised learning, as we'll see, it's modeling the measured features of data without some target. What that means is you're trying to extract structure from the data. You don't necessarily have a label that you're trying to predict. Sometimes you do this to understand your columns of data. Sometimes you do this to segment your customers in some meaningful way so you can market more efficiently. There's a lot of different reasons why you do unsupervised learning. So supervised learning, as we'll see, is when you have the features matrix, i.e. your columns. Home prices would be a target, so to speak. But features are basically just characteristics of what you're trying to understand. And number of rows is n, which is essentially how many houses you're trying to study, essentially. So in the case of the iris data set for predicting flower species based on the characteristics of the leaves, essentially, well, if you have 100 rows, what that really means is you have 100 different flowers that we say the characteristics of. They want to predict what flower species it is. That'd be our target. And of course, our unsupervised learning, we don't have a target. We're trying to extract meaning from the data. As far as today, we're really just doing from theory to really application. I would say we're more on the application side today, but the goal of today is really to mix a little theory plus diagrams to give us the why. So understanding essentially how models learn patterns from data. And we'll see this diagram later on today, so I won't really talk about it, but essentially understanding this diagram can help us with the actual application of the code. Because as I mentioned earlier, a lot of now is really just understanding basic syntax and basic concepts so that you don't have an error on either. Syntax is pretty easy to spot if you have an error because your code won't run. As we'll see today, I'm sure I'll have some code that I have from a while back that I just didn't bother to run that I want to include last minute in this presentation. But that's a syntactical error. And we'll hopefully encounter one so I can actually show you. And there's also conceptual errors. Are you trying to use an algorithm that's meant for classifying something as something or another? I gave the example of this can versus my phone. Well, that's a binary classification problem. If I'm using an algorithm that is a regression algorithm that's trying to predict between this or this, it's not going to work too well. So that's a conceptual issue. You might get code that runs perfectly, but you may not get the results you're looking for. So we'll kind of touch on that. And so the application really just shows us how. So turn that understanding into working code, because again, this code will run perfectly fine. But if we're not understanding the concepts behind it, it doesn't matter if your code works well if you're not solving the problem at hand. And one big thing for me, and I'll stop and look at questions in a second, is moving from the actual theory to the application. So when you're actually doing this, of course, we have some diagrams, we have trying to understand some equations. But the way I actually try to tie it together with the theory to the actual application is by having images that theoretically help with explanations. This is really important to me because oftentimes, if you don't have images to be able to understand yourself, it also hurts you downstream if you, let's say you understand something perfectly well. Well, are you able to explain that well to a boss or someone else? Pictures are worth 1,000 words or something like that. There's some quote like that. And the reason why I really recommend you get better at visuals or work with visuals is that in life, you need to give presentations like today. I'm sure you appreciate in theory that I have a lot of images to share. And as far as why we're using Scikit-learn for machine learning today, I mean, frankly, this is not a long talk. And I want to be able to quickly translate the theory to the application, so to speak. And programming machine learning algorithms from scratch is really just no easy task. I'm literally reading out the slide here. And the reason why I have this here, and I really want you to remember this, is your goal oftentimes is not to come up with a new algorithm. That's a very small subset of people that end up doing that sort of work. Most of the time, you have to actually use existing algorithms. Maybe you're going to improve them a little bit, but doing anything from scratch is not really pragmatic in 2025. And so if you have algorithms that you can use an instance of an algorithm someone else programmed and modify it for a use case, that's going to be a good use of your time. And that's why we use Scikit-learn, because there's a large amount of efficient, well-programmed algorithms, and that it really allows you to try multiple algorithms quickly. This matters a lot because sometimes one model performs a lot better, and that model happens to be okay for your given use case. Every algorithm has its benefits and drawbacks, not just in terms of accuracy or R-squared, whatever metric you want. It's also about, is the algorithm understandable, and so on and so forth. And finally, we use Scikit-learn because it plays well with other libraries, NumPy, Pandas, Matplotlib. And finally, because the library is popular, hopefully it's useful in the job market. Hopefully it's useful with getting help when you need help. And additionally, one thing I want to emphasize as we kind of go forward here is that if something's popular, does anyone know what a downstream effect of a library being popular is? Anyone have a thought? Why is it important that a Python library is popular when you need help? Feel free to ask. There's no real wrong answer here. So yeah, Nathan, there's a lot of developers, there's a lot of community support and bigger community. And then one thing I want to mention here is that on GitHub, I have the code for today and we'll go through it, right? But the one really important thing is that this is a public repo. How do you think modern large language models are trained these days? So yeah, there's a lot of maintainability and that stability for future implementations, all that stuff. But in 2025, one thing that's really true is that to train a lot of large language models, they scrape the internet. And I have a public repo that allows them to do whatever they want with my code. Well, I'm helping train some model in theory downstream. So it's going to use some of my code in theory, assuming it works well, to improve models, basically. So when I ask a question into GPT, it's going to do really well in terms of answering my question because it's seen a lot of Python data. It's also seen a lot of README data, which is another story entirely, which I'm happy to talk about in a Q&A session. But yeah, thank you for all the answers. It's pretty awesome. So let's get down to the actual code part and kind of connect the pretty images, a couple equations to actual results, so to speak. So what I'm going to do, and of course, please use whatever method you have to keep up, to follow along, is I'm going to activate an environment. This environment you don't necessarily need. I just work typically in Python environments to make it so if I ever want to have a project or even today's session, I have working code. Well, I want to run forever, right? If I have like 2 years from now and there's Python 4 or whatever, 5 years, I still want to be able to go back in time and theoretically be able to run this code. So I work in environments so I can go back in time and work with the same code. Because libraries change over time, right? Okay. So I open Jupyter Lab, and you can open VS Code. You can open whatever you want to be able to follow along if you like. So the one thing I want to first mention is, rather than starting with the notebook, is starting with setup, right? So what we had over here, and I think I mentioned this before, you can follow along either through Anaconda or any basic Python installation of any sort. The reason why I had Anaconda is because I've been working with it for years, and I basically have all the libraries I want. There's good and bad for it. Like, it takes a lot of space. It's really harder to share than with Google Colab. But if you want to use Google Colab, you're welcome to. But that's not really the main goal of today's talk. That'd be more like a basic Python kind of workshop. But having said that, if you have questions after the session, I'm happy to help debug with you, because I used to make tutorials for more or less a living. So, okay. So now what I'll do is I'll actually go through and start with the notebooks. One of the most, I would argue, boring parts for most students that land up working machine learning is we have a lot of really cool things we want to do. But one issue that we have is we still have to structure data that would be acceptable for a machine learning algorithm. What I mean by that is algorithms expect data in a certain format. They also expect, depending on the algorithm, your data to be structured in a certain way, cleaned in a certain way, not have missing values, those sort of things. So in this quick notebook, one thing I want to do is I want to basically quickly go over how to arrange data into a features matrix and a target vector, i.e. the target's what we're predicting, and the features are just characteristics of our data. So in this example, we have flower species information, sepal length, sepal width, petal width, sepal width, let's say diagram. So these are just really just characteristics of a flower. Understanding this is not essential for this notebook or any other ones, if I use it in any other ones. So what I first want to do is I'm going to restart my kernel and clear all outputs. I'm doing this because, well, frankly, before I came to today's lecture, I should have just cleared out outputs if I want to be, simple, or to make it like more efficient. But like anything, the first thing you have to do in any sort of analysis is you have to import libraries in Python. So that would be import Matplotlib because you want to be able to visualize things later on. Import Pandas because you want to be able to manipulate data and structure into a format that's acceptable for an algorithm. And then we also have to import a data set. So for this one, it's not some external data set. It's inbuilt into Scikit-learn. And that's one thing that I think is relatively important to do. It's like go over very basic things so that the harder stuff is going to be more understandable. And we'll get into the theory for linear regression in a little bit, by the way. So we're loading data into the Iris data set. we're putting into a Pandas data frame, and then our target is going to go into the column called species. And this is going to be relatively simple. And we have, of course, 4 features that we're going to use to predict the target, which is species. One thing I want to mention here is, as far as like one thing you'll see in theory, like very, very commonly, is you often find your X denoting your features, and you'll find your Y denoting your target, what you want to predict. If you have a math background, one thing you'll kind of remember is that if you actually write out mathematical notation, typically you have a capital denoting a matrice, which is like 2-dimensional nature, and then you have lowercase denoting a vector. So this is a matrice, and this is a vector. So this is our target vector, and this is our features matrix. So that's often how you hear people talk about features matrices and target vectors. Questions so far? I think this is relatively on the simpler end. Okay, Ram asks, is it right to say LMs are trained using unsupervised learning, and then while fine-tuning, we use supervised learning with a specified labeled data set? So it's a little above the context of today's lecture, but a lot of LMs, you can think of them as it's a form of unsupervised learning initially, and then they use a form of reinforced fine-tuning or reinforcement learning from human feedback, where in theory, there is some feedback going back into the LLM, and that's to align it with human preferences. So I'm happy to share that sort of stuff if you're kind of curious. So one thing that you see OpenAI do these days would be something like this. And please, everyone else, this is like not pertinent to the conversation, but I think it's always nice to kind of talk about and kind of grow from each other, right? So yeah. And one thing I want to mention here is, like, no one really shares how a lot of the LMs are trained, not in too much detail. They give as much as they possibly can, but a lot of these models are trained on information that they probably should not train on in the first place, in my opinion. So it's basically there's a lot of copyrighted material is kind of what I'm trying to get out there. So as far as how you create a model from Scikit-learn, let's start with something very simple, like a linear regression. So what we see here is a linear regression line with an equation y equals 1.58x plus negative 50.99. And then the reason why I'm mentioning this is that this goes back to the slope-intercept form you probably learned about in grade school, y equals mx plus b, where your m is this 1.58 thing. X is basically when you put in a number, you can use any sort of value in your x-axis here. And then your intercept is where it crosses the y-axis here. And this is simple. And most of you probably done this if you haven't done this in Python, most of you have probably done this in, I don't know, Excel, any other tools you possibly use over time. So that's one really important thing I want to mention here. Well, one really important thing to do first, like anything, is if you want to turn something that looks like this into something you can code from scratch, well, you have to first import libraries. Good common practice is to have imports at the top of your code. It's very commonplace. If you use GPT, by the way, to help you with the basic code, please don't have random imports further down your notebooks. It's really bad practice I'm starting to see now, where people have something like this, and it's just not very professional. Also makes debugging a little bit harder down the road. So right now, we're going to import our model from Scikit-learn.linear model, import linear regression. And then from here, we're going to load our data set. One thing I kind of want to mention here is this data is pretty normal. It looks like an X and a Y. And the Y's I want to predict. I'm not even telling you what the Y is. It's just the target. It's what I'm predicting. Like anything for Scikit-learn, though, you could be using the most complicated algorithms, and you'll probably still have issues if you don't deal with your data issues. So in my y-axis, I just happen to have 8 missing values. One thing that's really important to always consider when you're working with data in general is that you have to figure out the missing values. Sometimes you can actually drop them. Like if they're missing at random, you can drop them typically because there's no pattern in the missing data. If they're not missing at random, you probably have to find some way to not lose information that'll be useful for prediction downstream. Sometimes if there's some data missing, that could actually be a feature if you happen to be predicting something else. In this case, I'm predicting the y and it just happens to be missing. So what I'll end up doing is I'll end up dropping those values. Again, be very careful with this because if you have a lot of missing values, you might want to improve your data. You might want to fill them in. You want to understand why they're missing. It's not just something you can just forget about, like I'm doing right now, basically. Hypocrisy is real. And then so from here, we could, of course, use the fill in A method on the Pandas series if you wanted to, but I thought it was just easier just to remove them for now. And so from here, you have to arrange your data into a features matrix and a target vector. So from here, if you look at my data, I have it in a Pandas data frame. This is a type of a data frame. For me, I'm a little bit old-fashioned. Back in the day, Scikit-learn would expect data in a NumPy format. So what values basically does is it basically converts it into a NumPy array. And I'm putting it into my variable x. And one thing you need to know is that your features needs to be two-dimensional. So even if you have one single column, your x needs to be two-dimensional in nature. So if it was 94, nothing, most likely Scikit-learn would throw an error unless they fixed that issue recently. So for y, it's okay that our y is a vector because it does need to be two-dimensional for this use case. One thing I want to mention here, of course, is that in Scikit-learn, I already imported the model I want to use. But in general, Scikit-learn follows a four-step modeling pattern where you import the model you want to use, you make an instance of the model you want to use. And in this case, when you make an instance, all you're really doing is basically saying that, like, hey, I like the code that you have. I want to set some values for some hyperparameters. And for linear regression, there's really not many hyperparameters. The only thing you can really set before fitting the model in the data for this basic version of linear regression that we have here is whether you want the intercept to be true or false. So what I mean by that, if you can see this image here, on the left, we have a model with an intercept, and on the right, we have a model without one. And one thing you might notice is that this thing on the left here, let me see if I can make this a little bigger. Oh no, I will open the image separately so I can show you a little bit better. And one thing I want to mention as I go through here is I spent a lot of time on these images way back in the day. But for this image, reg intercept true false is right over here. So when you actually look at this image, like the model on the right fits a lot worse. So basic things like setting hyperparameters to some value, or I should say, yeah, hyperparameters before you fit them on the data, it can really make a big deal. So the basic things you can do right now make a big difference. And by default, I believe fit intercept equals to true. So you're not going to have this issue for linear regression, but you'll have this sort of issue with some other models down the road. And we even have that today, by the way. So make an instance of the model with my intercept equal to true. And of course, one thing I recommend you do always is you may not be familiar with documentation of a model that you want to use. Oftentimes people have really great inbuilt default values for things, but there's a lot of other things you can kind of understand about what you can set in your model. So if you're using gradient descent to come up with a linear regression model, well, maybe you need to look at the tolerance if you have some sort of issue. If you have something we'll come across later today, if you have multiple cores on your machine and you have a very complex model, you can set n jobs equal to some number based on how many cores you have on your machine. So for my core, for example, this is really overkill for linear regression, right? By the way, like it's not necessary. So for me, if I look at my system report, I can see that I can't make this bigger, but I have 16 cores on my machine, 12 performance and 4 efficiency. So in theory, I can speed up my computation, because one advantage of scikit-learn is it's easy to use. One disadvantage is it's not very parallelizable, even across the cores in your local machine. And we'll get to that later, by the way. That's something we'll definitely cover. And so from here, you can train the model on the data. And so what's really happening is the model's learning the relationship between my x, my one column, and I want to predict. So in this case, it's learning the relationship between my one column and my one target. But normally this would be like characteristics of the house, and then y is the price. So it's learning characteristics between whether it's on the waterfront or not and the actual price. And this happens in place, by the way, so you don't have to assign it to any variable. And of course, what you can do is, let's say you have a given x value. You can use that x value and you can input into your trained model to then make predictions using said trained model. And this is relatively simple, but I really think the fundamentals matter, and it helps you deal with less issues down the road. As far as how you measure model performance, for regression problems, it is with R-squared. And we'll talk about that metric and the actual equation of it, and what it actually does in a future notebook. So you use the score method, and we find out the R-squared is about 98, which is pretty good. But I have a very simple data set. And truth be told, about 10 years ago, I generated the data, and I removed some values just to have a nice, very, very simple thing to do. Which gets me to my next point. If you're doing anything with a very common model, something that has parameters that you can basically output to then be able to explain a model, in a lot of fields, it's actually really important to be able to explain a model, like how it works, why it works. If you increase an x value, does the prediction go up? If you decrease, does the prediction go down? Like, those are really important things to be able to explain to people. And I don't think that gets enough attention, as we'll see later today. And from here, of course, you can plot your best fit model. And this is just with Matplotlib code. I encourage you to go through this notebook later on. But of course, you can do the same thing I did earlier and plot with and without an intercept. So the next thing I want to go over, and hopefully I'm not going too fast. How is the pace? I can also go faster if you want. It's a shame I can't get a up or down kind of thing. But let's now go on to train test split with scikit-learn. So for this notebook, if you don't want to go through and run everything, I really find this is a, oh, Janice, I can slow down then. Okay. So to kind of reiterate here, and I need to actually make sure I have the data for this one. One thing I kind of mention is that I have quite a few examples of ways you can kind of practice what we're going over today. So if I'm going too fast for this linear regression, you could always go back and kind of use a similar example. This is with a mollusc data set where essentially it's characteristics of an abalone, like an actual shelled creature. And it really just like shells, basically. So I'll update the repo to make sure everything works 100% perfectly well. But what you'll end up finding is that it's really the same process no matter what type of data set you have. You make sure that, to kind of reiterate, you import the models you want to use, you get your data. This is data that I happen to host in my GitHub. And then you go through and you basically clean out your data, making sure that you remove the missing values or you fill them in. And then from there, you range your data into a features matrix and target vector. And in this case, I only use one feature, even though there's many. I did a very simple linear regression model, very, very similar, and the model did perform very well. I had an R-squared of 0.31. Well, one thing to kind of mention is, like, sometimes you have models that have a linear relationship between your features and your target, but sometimes the relationship is a lot more complicated, and you can't really understand the relationship with just one feature X predicting, one feature or one target Y, essentially. Because in this case, I'm only looking at one feature that predicts one thing, right? It's not really related to real life. So one thing I kind of want to mention here is like, we can go over this if we have like a little bit more time. But essentially, if you put more features into a model, before I had one feature, oftentimes when you put more features, you often get better performance. Before I had a performance of like 0.35 or something, or 0.3, and then putting more features in this particular notebook, which you can go over later, it goes from 0.35 to 0.5 to 0.75. So it's better in theory, right? But the other thing I want to really mention with this, though, that's one thing to really like emphasize, is that you don't always know that there's a linear relationship between your features and your target, what you want to predict. So going on to the next notebook, and I will slow down from here, no problem. So for train test split, let's go through one thing I want to mention. So with this linear regression notebook, one thing you might have noticed is that if you actually look at my data set, and I'll scroll up very slowly, I had one column my X and one column my Y that I put into a Pandas data frame. This is just a nice way to store data. And I went through and did the whole cleaning process and all that sort of thing. But one thing I didn't do that's very machine learning-like is I ran my data into a features and a target. Cool. And then what I ended up doing is I had the model learn the relationship between all of my X and all of my Y. The issue with that is in real life, we want to be able to use machine learning to make predictions on data it hasn't seen before. When I fit the data on the entire data set, it learns the relationship between my X and my Y. And then what I was doing over here was I was making predictions that are not really out of sample. And I'll get to what the in sample and out of sample thing means in a second. But this is why in machine learning, we have something called a train test split. And the goal of supervised learning is really to build a model that performs well on data it hasn't seen before. And that sounds nice in practice. Is I make a model, I train it on all the data I have, and hopefully it'll do well on data it hasn't seen before. Well, in real life, I don't have new data I haven't seen before. I can't get data from next week and validate that my model today works well. That's one common issue that we have. So does anyone know what kind of procedure you would do to simulate new data that you don't have yet? So my question for everyone would be something like this. And by the way, the answer is kind of on the screen. So just trying to see if people are following along. A goal, yeah, we have testing. And of course, there's ways to make sure your model performs well and things I haven't seen before. Yeah. So Matthew and Roshan and basically said like there's some sort of typical split where if we have 100% of our data, because that's the data we have in our machine, in our features, this is our X, a feature is X, and our target Y. Well, I want to simulate data I haven't seen before. So one thing you do is something called a train test split. And what I mean by that is something that Roshan basically said, or Matthew said, is that we split about 80% of our data into our training set, and then roughly 20% into our testing set. This is something that's true for traditional machine learning. It's probably less true for modern day large language models, because for a lot of traditional machine learning algorithms, this has worked very well in practice for many, many decades. But for modern day large language models, you basically don't need a lot of data to validate on, because you basically train on the entire internet. And so the world is your training set, basically, and your testing set. Okay, so what you do for train test split is we randomly sample. And then we split our data into training and testing sets. What I mean by that is, let's say row 0, like one house, essentially. The first house goes into our training set. The second one goes into our testing set. and about 80% end up going row-wise into our train set, and then 20% go into our testing set. It's important to mention, though, that we make sure that house number 2, those features, and the corresponding price of said house go into both those things go in that same row into our testing set. And the idea here is that you use your training set for training, i.e. the fit command. And then after we have the model learn the relationship between our X train and our Y train, then after that, we basically put in our X test and make it output predictions and compare it to the actual Y test, basically our home prices. And we'll get to this in a bit, because this is the theory of train test split. We'll actually get to the actual application right now. So again, the whole point of this is that we want to simulate how a model will do on data it hasn't seen before. So we kind of have to make a situation where we can kind of evaluate how the model would theoretically do on data that data it hasn't seen before. You want to make the model generalize on data, essentially. And one problem they often see in real life is the consequences of not using a train test split. So you can have an entire data set. I arrange my data into our features, i.e. our X, and our target Y. We use all of our feature and target information for training. We use that same information for testing. The problem with this, though, is that oftentimes you have a model that basically memorizes the training set and won't generalize well to information it hasn't seen before. And that's really important because you want your model to be able to generalize. Okay, now let's go into how to actually do this to train models using Python. So we go from basically from getting our data offline to cleaning our data, selecting features, to performing a train test split, to hyperparameter tuning. We'll talk about what that means in a bit. A decision tree regressor to predict home prices and more. You might be wondering, what's a decision tree? Well, we'll get to that actually in our notebook after this. One thing I kind of want to show you is that in theory, it's very possible to use models that you don't know or understand. It's probably not a good idea in practice, but the Scikit-learn API is very simple. So I'll go over how that model works in a second. Yeah. So in Python, one reason why we use Python in particular is that we want to be able to import libraries. This is perhaps the most important part of using Scikit-learn, honestly, or sorry, using Python, is we don't have to reinvent the wheel. So I import Pandas and NumPy because I want to be able to manipulate my data. I have Matplotlib because I want to be able to visualize my data. And then Scikit-learn is just a library for having easy access to machine learning algorithms that I can essentially use very similar syntax to run multiple different models. So much so that I decided today, as a bit of a test, to basically go over train test split first, and then go over decision trees, the model we're actually using in an earlier notebook, because I want to be able to prove a point, basically. Okay. So I do shift enter, I run that cell, and then I'm loading a data set from online. And this is a home price data set where houses were sold in King County, which is like Seattle, between May 2014 and May 2015. So there's a time range where this data set was gathered. And you can download the data set from Kaggle, or you can load from my GitHub. Because I give a lot of talks, I stored an extra copy of it on my GitHub in case Kaggle ever goes down. And so what we're seeing over here is I have 5 different features that I downloaded, and I have the price, which is what I want to predict. It's important to mention, though, that this is something I did for convenience. It's not necessarily the best practice. So if you look at this, there's obviously a lot more columns. There's 21 different columns. Some of these columns are useful. Some of them aren't. But it's your job as a data scientist to be able to inspect your columns, see which ones are better, see if your model is learning what you think it should be learning, and go from there. Okay, so I'm basically going for a subset of features right here. And then from here, we're just arranging our data into features and target. So what we see over here is the same 5 columns we had before in our data frame. So our data frame right now looks something like this. As you can see, it matches this pretty little image where we have bedrooms, bathrooms, square foot living, square foot lot, number of floors, and then price. We have our data frame, and all this code is basically doing is we're separating out our data frame into our X and then our Y. Anyone have questions about this so far? Oh, let me see. Okay. Feel free to ask, and I'll come to it very quickly. So what essentially ends up happening for our X train and X test, this is our original data frame before we split into our X and Y. And based on your random state, which is some random number, essentially in Python, well, you're going to split your rows. This top row is going to go into our training set, or these 2 top rows. This third one's going to go into our testing set. This one's going to go into our testing set. And this one will go into our testing set. And roughly, by default, in this case, 75% is going to my train set, and then 25% will go into my testing set. So this entire row is going to my testing set. And then if we're actually running the shape command on this, one thing you would notice, and let me make this a little bit bigger. As far as our X train, so if we have 21,000 rows starting out with, and you multiply that by 0.75, you'll end up getting around 16,000. And then the remaining number of rows go into our testing set. And one thing you'll notice is that we have 5 columns because it's basically just information from our X. It just happens to be different rows. And then in our testing set, for our Y value, we just have our prices basically. It's just the price information. It's important to mention that basically, if you just ran this code without random state here, you get different results every time for which information goes into your training set and which information goes into your testing set. That's a normal thing. Because we're doing a tutorial today, I set the random state equal to 0 because I want you to be able to replicate the same results I have. So you can follow along in theory if you want to. So the next thing we're going to do is I'm a little bit of a hypocrite here in the sense that I said that we typically import models at the top of our notebook. For demonstrational purposes today, I'm basically going through the process of importing a model I want to use. I'm setting some sort of hyperparameter values. We'll talk about what max depth equals, what that actually means in the next notebook. We're making an instance for a model. Does anyone know what an instance is? That's actually one thing I want to ask. Is this any considerations we need to have? Are there any considerations? When do we split it? So you split your data after you cleaned it. It's probably one of the biggest things. When we get to logistic regression, which is why we cover it later, which is not normal, I think, for a talk like this. The reason why I'm doing it later is that there's additional processes we have to do to clean our data properly for a train test split. So my question is, what is an instance of a model in machine learning? Yeah, so what Mr. Shi said, a specific model with set hyperparameters, absolutely. So when we're working with a machine learning model, a decision tree or linear regression or random forest, which we'll learn about later, well, there's a lot of characteristics that people have already coded. Like for instance, on the image obviously on the screen here, we have a blueprint of a dog. A dog typically has some sort of properties. A dog typically has eyes. They typically have colors. Dogs typically have a height. I think every dog has height, length and width. And in theory, dogs can do a lot of different things. They can sit, they can lay down, they can shake, they can come to you when you call them, except for my dogs, especially on the couch when they're old. But when you make an instance of a model, you can basically define those properties, whether it has a certain eye color, whether it knows certain things. In the case of machine learning models, we can set how much we want the model, some specifics of the model we want. For linear regression, we said that, hey, you know what? I know a linear regression model can have an intercept or not. In this case, I want the intercept. And that's what we set when we were making the instance of the model. For decision trees, that's how many splits it can make before it makes a prediction. And we'll get to what that means in a little bit. I'm kind of going application back to theory to tell you about how important the theory is. So import the model. I'm making an instance of the model. And then I'll train the model on the data where I'll learn the relationship between my X train and my Y train. These are information about a number of bedrooms, bathrooms, or whatever for a given home price. It's learning that relationship. And then I can make some predictions based on that information. So for next test, what we're really seeing here is something like this. So for our first example here, for 2 bedrooms, 1.5 baths, 1,430 square foot living, all this stuff, number of floors 3, we have this kind of question for a decision tree. What is the price of a house with the following features? This is what our trained model looks like, and we'll talk about what decision trees actually are in a second. So really what this model ended up doing, what it ended up learning, is that the first question asked, based on how I trained this model, is the square foot living less than or equal to 3,415? If that's true, I'll then ask the question, is it less than or equal to 2,259? And if that's true, based on how many houses are in this leaf node, so to speak, we average those predictions together, and we'll have that as our prediction. This is a terrible model. The price prediction is 406,000 based on the average price of 10,527 houses contain the leaf node. But this is also why the theory actually matters, because when we have a result that may not be that good or that interesting, you can kind of be able to debug and learn the theory, and then you can kind of do the application. If the model's too complicated, sometimes it's worth these days just seeing if the model actually runs and then learn the theory of the model to make sure you're not wasting your time. But for simple models like this, it's really good to actually know the theory, which we'll come back to in a second. But as far as how you measure model performance, we had that R-squared thing earlier from linear regression. Like all the way back here, we measured our model performance using an R-squared, where a model that always predicts the mean, essentially, will get an R-squared of 0. And the highest possible R-squared is a 1. And the reason why that's true is we have this equation. It looks really scary, honestly. R-squared is equal to 1 minus the summation of your true value minus your predicted value squared for all your samples. So if you have 100 rows, you basically just take the difference between the predicted minus the actual squared, and then that's over the true value minus the mean value of your observed data, essentially. And the reason why this looks really scary is all this model performance is basically telling you is how accurate are you predicting something versus the actual true value, right? These equations look scary, but when you actually think about it, all you're really measuring is just the difference between the true minus the actual. There's a lot of different formulas, and every metric has a benefit or drawback. But I really encourage you not to be too scared of these sort of metrics. And if you're a little bit ever lost about like, oh, I've never seen formulas before in 20 years, And that's okay, by the way. I went back to school after 10 years of doing machine learning in industry, honestly, and a lot of teaching. And it took me a little while to get used to seeing mathematical notation everywhere, but it's not very scary if you just put in one number, put in two numbers, and then see if the R-squared goes up or down. It's actually a really good way to learn. And so that's all this reg.score is doing. I have my instance of my model, I use a score method, and by default, because I have a regression type of problem, it'll give me an R-squared for this particular problem, because it's regression. I'm predicting a continuous value. And my R-squared here is 0.438. Well, what that's really saying, though, is I don't really have a good model. It's actually pretty terrible. One thing that a lot of you probably would notice if you had time to kind of go through these notebooks before the presentation is if you actually scroll up here, you can actually do things that someone like me that's making the machine learning model clearly forgot to do. And that's actually understanding your data and understanding the problem that you have. So the data I had that I put into the model essentially was bedrooms, bathrooms, square foot living, square foot lot, number of floors. What type of features did I not include in the model? So what type of features typically determine home prices? Besides, square foot, besides square feet, besides, number of bedrooms. So Denny's has a good thing. He said location. Roshan said something that leads into the next question, categorical. So what are important things about location? Is it just the latitude, longitude? Are there common things that are associated with location that people care about? School district, yeah. Location, type of house, community, country, yeah. Walk score, very important, especially if you live in certain cities. Yeah, proximity to schools. These are all amazing things. And that's one thing I really want to empower everyone with today as we go through as much as we possibly can, that all these sort of things are things you should probably include in models. And if you find that you're training a model and doesn't include things that you find very obvious that a stakeholder might care about, the people that pay you essentially, well, you may want to gather more data. You may want to look back into your data, see if you can add more features. Because one thing I did for convenience here is I had all these columns. I went through all this effort, and the theory is fine from, I didn't have any coding errors as I went through this. My machine learning logic, I didn't go through this with everyone yet for decision trees. I skipped over it. But one thing you might have noticed is that all seemed fine, it seemed to run well. And I had an R-squared that's reasonable. Well, actually, it's pretty terrible. But I didn't include things that you normally would have. I didn't include, is it on the waterfront or not? This is a binary column in this data set. The view, the condition. So someone mentioned here year renovated. So maybe you can make a feature based on the year built minus the year renovated kind of thing. Yeah, you can figure out a metric for that. Like how long has it been since it's been renovated is probably a feature. So if it's new house, well, most likely it hasn't been renovated yet because it's a new house. Maybe you can find some way to have a nice feature like that. Zip code. Well, the problem with the zip code is you have to actually tie it to something interesting. So if you have an address, maybe you can do the kind of thing that, let's say, who was saying this? Samarath, and Ashwin and Denny said, and Samarath actually, what's the distance if you want to walk to school? What's the distance from a Costco? What's the distance from, whatever? What county is it in? I know for certain people in certain locations, they care what county it's in based on taxes, based on how the county's run, all that sort of stuff. So I just completely ignored it. And I will continue to ignore it, actually, in this case, because I want that to come up later on in the notebook. So what I'll do right now is ignore the message I was trying to give you. So let me go through. Okay. So of course, one thing you could do with some models that we'll get to is that you can always try to visualize your model. Some models can be visualized like this, and that's why I started with it, because I fit them all in the data, and then I create a visualization based on the model, so that people can, in theory, understand the model, like how it goes through its logic of making predictions. Can anyone tell me what industries you're more likely to have that people care about understanding the predictions? Like, what industries do you not care about how the predictions are made, and what industries do you care how the predictions were made? What industry and use cases do you care how the predictions, how the machine learning models make predictions? How explainable the model is. So one thing Samar said, and I'm sorry if I mispronounced her name, is insurance. So if I'm denying you insurance coverage, well, I have to be able to give you a reason. Maybe that is because you're next to a lot of wildfires. Maybe that is, something else about your credit history. Finance, certain types of finance you do care. I'm a machine learning for finance PhD student. So for things like credit, absolutely. If I deny you credit, I have to be able to say exactly why the model is denying you from credit. And so for disease prediction, if I'm telling you have cancer, you probably care about why I think you have cancer. For those type of problems, I would say for disease, sometimes you want to do some sort of trade-off that we'll get to when we get to logistic regression today. And we will get to it, I promise you. And so, yeah, mortgage approvals, that stuff really does matter. So really consider that, depending on the industry you work in. And so one thing I kind of ignored, and I was hoping that everyone got, which everyone did, is that I could have done a lot of better things with the model I had, assuming the model would actually learn from it. And what I ended up seeing over here is that this is a map of King County, which includes Seattle, including Redmond. I used to live out here somewhere. And one thing I found is that the prices were a lot more expensive. And this is just visualizing the price based on latitude and longitude. So below a certain point, there's some sort of line here. You can have some sort of complicated line here. The prices are a lot cheaper versus, downtown Seattle near Microsoft and Google. And actually Microsoft, definitely. Amazon was in the big city for a while there. And there's a lot of other companies here. But down south near Tacoma, there was less companies. Although most of you can probably tell me what companies were in Tacoma for a long time. Assuming this is Tacoma. I'm not very good at geography. So the next point I kind of want to mention is that with machine learning models, we can tune them as well. And the R-squared for this model was 0.48 or 0.438, yeah. We can always, improve the model performance. One way is, of course, to get better data. And one way that we'll kind of talk about is to essentially tune our hyperparameters. And one thing people often get confused about is essentially hyperparameters versus parameters. For a given model, if you have to specify model parameter manually, then that's a hyperparameter. That's what we set before we fit our model in the data. So going back to the top here, I'm just going over definitions right now, and we'll get to the actual machine learning part. This is a hyperparameter because we set it before we fit our model in the data. And then one thing you can do afterwards for something like a linear regression is we have a parameter, and that's something that comes out of the model after we fit the model in the data. So when we have these parameter values over here, this is our slope. This is a parameter. This is something we got after we fit the model in the data. The thing we set before we fit the model in the data was our intercept, whether we want to intercept or not. And that was set Was set way above. So I think this was under reg. Yeah. This was set way, way above. Sorry. Fit. You can tell the images don't always look good in Scikit-learn anymore. Okay. And then going to the next part, we can do hyperparameter tuning. And this is kind of where the learning kind of comes in. The definition from Jake van der Plas is essentially the learning of machine learning really comes in when we have hyperparameters. They're essentially learning from the data. So what we're doing over here is a simple for loop. For this parameter, and I'll talk about what it means to death. Sorry, I shouldn't say that. I'll talk about it in extreme detail, where we essentially we have a list of values from 1 to 24 in this case, for max depth range. And we're going to iterate through this for different values of max depth. This is a hyperparameter. We don't know what it means yet because we haven't learned the theory. And we're going to make an instance of our model. We're going to fit them all the data, and we'll get some sort of scores. One thing I want to mention here is that when we actually run this, we end up finding something kind of interesting. So the model performance on the testing set seems to be pretty good for, let's say, max depth of 5, despite the fact that I've only fit 5 columns on this data. It's not the best. And then one thing you notice is that when I make max depth really high, the performance goes down quite a lot. It's even worse than, way over here. So this is not the best Python practice. And if you're curious, I really recommend you go through these notebooks in detail and spend a couple hours on them. But what you end up finding over here is something called the bias variance trade-off. And don't worry if this code seems like a lot. Part of the reason why there's so much code here is I want to be able to explain something through visuals. So in order to understand why max depth of 5 was the best model for our data, you can basically take a look at the graph below, which shows the model performance when tested on the training and testing set. So this code is just advanced Matplotlib, and you can get this from GPT. You can also just do it yourself if you really love graphing things. And what we end up finding over here is that we train the model on our training set, and we evaluate it on our testing set. And we end up finding the best model for us is when we have a max depth of 5, because all we really care about in life is how well a model generalizes to data it hasn't seen before. It's really easy to have a model memorize something and not do well on data it hasn't seen before. So what we find over here, when we essentially let the model grow as much as possible, max depth is essentially, we'll talk about this in a second, how many questions you can ask a model until it comes to a prediction. And essentially, when you let max depth be very high, you can have a very complicated model, is essentially what I'm saying here. And it can essentially memorize a training set, which is basically doing over here. You have a model that goes from, let's say, 0.3 something at a max depth of like 2, to when you allow the model to grow like really, really complicated, really, really big, well, it does really, really well on the training set, and it does really well on data it hasn't seen before. So what people often say is that this is the bias variance trade-off, so to speak, where we essentially have a point where having a model be, there's a trade-off between having a really simple model and having a really complex one. And you want to find the point where the model performs best. And that's usually somewhere between a complicated model and a really simple one. It's really an easy concept to understand. So of course, there's other model simulation type of techniques, model validation techniques. There's something called k-fold cross-validation. And I'm not going to cover this right now because we have like an hour, essentially. But what I really want to talk about here is that when you do a train test split, the one major disadvantage of this is that we only have so much data. I only have so many houses in King County and Seattle from that time period. Well, there's different ways to do things where you essentially break up your training data into multiple different folds. So you can basically have a model learn some relationship between more data, essentially. The one advantage of this really is that when you do hyperparameter tuning, if you basically you have a holdout set, your test data, and you have all the hyperparameter tuning happening in a training set, well, in theory, you don't actually have information leak from the testing data into your training set, essentially. Because if you do enough hyperparameter tuning, in theory, you can do enough experiments that one of them seems significant just because you've done so many experiments. You do 10,000 experiments, there's a good chance something that'll look good, it may actually be good because of something called like p-value hacking, essentially. It's not quite true, but that's a good analogy for it. Okay, let me go on to the next notebook. Anyone have questions so far? Well, if you have questions, feel free to email me. Feel free to ask questions right now. And I'm always happy to kind of chat about machine learning because that's what I do. Okay, if you look at the schedule for the next notebook, we're actually going to get to decision trees. Of course. So let's talk about hyperparameters in extreme detail. That's kind of what I was getting to next. It's one of my favorite topics. Okay, decision trees. Did I actually include that here? Yes, I did. Okay. So let's go back to our friend decision tree, which I basically went through an entire notebook in a lecture that's literally called From Theory to Application. I started off with the application, and now we're going to go back to the theory. The reason why I'm doing this is multiple fold. One thing is that I want you to kind of understand that in Scikit-learn, you can basically use a model you haven't seen before, and that's perfectly fine. But the issue you often encounter is that you don't understand the underlying theory behind it, and you can have a lot of issues that you normally wouldn't have if you understand the theory. And so for a lot of machine learning models, it's really good to know some theory and also about like how interpretable the models are, what the hyperparameter values are, because like anything, right? So like one question you asked is like, can you tell how hyperparameters help? Well, by default, when you actually look at the code we've kind of been using, well, if I go back to our linear regression thing, I hate to go back and forth, but there's a good reason for this. For linear regression here, one thing you might have noticed is there's default values for these hyperparameters, essentially. And so by default, your value is set to true. For decision trees, let me open this one up. And they have a lot of documentation in Scikit-learn. It's nice, and it was really awesome back before we had large language models. And so one thing you might notice is that max depth is something we set before we train the model on the data. And the default value for this hyperparameter is none. And we'll actually go into what that actually means now. But I assure you that the default value that the Scikit-learn gives you is not necessarily always the best thing. The people that built these libraries, they implement the models in a way that the models will mostly work well out of the box. But in a lot of applications, you don't care about mostly. You don't care that a model does pretty well for your use case. You want to have a model that does the absolute best for your use case. So what you end up doing is you vary the values of these hyperparameters. And there's multiple hyperparameters for multiple models, by the way. And so you want to find the best values for these things that produce the best models that do well. So if you're predicting cancer on someone, you want to have a model that was trained properly so that you do a better job of predicting whether they have it or not, so that people don't get mad at you, basically. Or you don't get sued, depending on what you care about. So what we end up seeing over here is this is a decision tree that we kind of saw earlier. And the way they work is you essentially have decision nodes, which basically are decision trees. You can define them as a series of questions designed to predict a class, whether something is this can or my phone, or predict a continuous value. And so what we have over here is a decision tree for classification. And it basically says, like, yeah, if petal length is less than or equal to 2.45, if that's true, then it's a type of flower species called Setosa. If not, you ask another question, and eventually you get to leaf nodes or terminal nodes. And that's basically what the prediction is going to end up being. But you might be asking, well, Michael, I know what we're talking about here. You've told me before this is how we use a classification tree, or in the case of the housing data set, well, that's how we used a regression tree, right? We actually saw the actual predictions, like how it made actual predictions. So for this one, we ended up seeing that this is a decision tree for regression. And it was essentially, for a given value, we basically put it through the tree and made a prediction. Well, how do you find the given split points that actually came up with these questions? Is probably what you're going to ask. Well, that's what we're going over right now. So the way these things are grown is decision trees essentially learn a sequence of if-then questions, with each question involving one feature and one split point. So the way it works is the model first starts with a question like petal length less than or equal to 2.45, and it'll split into two branches. And the one thing you might notice is the way these models choose a split point is a good value is one that results in the largest information gain. Basically what that means if you have classes is you find a good point that splits the classes from each other. And ideally, if you have a really good split, you completely isolate one class from another. And the way these models work is they look at every feature and a variety of split points that result in the highest information gain for these classification trees. It's basically optimizing an equation. So one thing you might notice over here, though, is that for this first split, they result in a pure node, which means that I already isolated all these 38 flowers as Setosa, and I'm classifying that as Setosa. The problem here is if you look on the right, well, I split this class perfectly, but the problem is I didn't necessarily split out this versicolor and virginica. I'm classifying all as versicolor right now, and the model's not very good. Well, in theory, I can ask another question. Well, the next question can be, is the petal length less than or equal to 4.95? And I did a pretty good job. I separated out, and I have 38 examples that are versicolor and 3 that are virginica in this diagram. And what you notice over here is that I still have a little bit Guinea. So in theory, if I get Guinea towards 0 for each of these columns, that'd be a good thing. Well, what we end up finding over here, the tree has a maximum depth of 2 here. I have at most 2 questions before coming to a prediction. So the first question is petal length less than or equal to 2.45. Second one's asking about 4.95. And for simplicity for this example, I just had one feature that this model is trained on to make it easier to understand. And so this is a hyperparameter. I set this before I trained the model on the data. Well, one thing you might notice is that if you look at this diagram, well, I'm still not separating out perfectly. Maybe I can have another question. And in theory, you can have more and more questions, maximum number of questions before it comes to prediction allowed. And in theory, you can have a better model. So one thing to note here is that maximum depth is how much you let a tree grow. And that's a hyperparameter. Maximum depth is a hyperparameter. tree depth is something that comes after you train to model the data. And tree depth is a measure of how many splits a tree can make a tree made before coming to prediction. So one thing you might notice over here is that this is 1 question at max, this is 2 questions at max, and this is 3 questions at max before coming to prediction down here. And as far as how these models select the split point, it really depends on the metric that you have. And I mentioned before, decision trees for classification, splitting the feature and split point, the results on the most information gain. And the way this works is information gain before splitting minus information gain after splitting. And if you're curious about the terminology here, the way this works is you call A the parent node of the child nodes B and C. And of course, there's formulas for this. And if you're curious about how this works, you can plug in numbers. And this may seem like a little bit much, but for all these sort of metrics, one thing you might end up finding is that you can, of course, use set different impurity criterions that determine how you split the models. But for this particular model, what really ends up mattering is actually just how much you let the trees grow. So in practice, no one cares, essentially is what I'm getting to for these formulas. But if you're curious and you want to take time to do this, you can actually just go through, and I have the formulas here for a given tree, and I manually calculated information gain using Python. So it's useful to know for this case, but the more important thing I would argue is more so about tuning the hyperparameter, which is max depth, which is how much you let the tree grow at maximum. It doesn't mean the tree will necessarily grow infinitely. And the reason why it won't grow infinitely is if we have this example up here where I have Setosa over here, and let's say you forget about the versicolor and Virginica. Well, if you have a pure node, you can't split any further. So if you have a model that perfectly splits out your classes, it's not going to keep on asking questions because it's kind of pointless. The algorithm stops. The trouble that you end up running into is, for an example that we saw earlier for this train test split, when I looked at this graph here, is that the model was allowed to ask a lot of questions. And that worked really well for the training set because I was able to isolate every single house from each other, essentially. Well, the problem with that is I asked too many questions, and that overfit on the training set. It did really well at predicting information on things I've seen before and learned a lot of relationships really well. But that information not generalized well to the testing set because I had so many questions. That's one really important thing I want to mention to everyone is like there's syntax understanding of like Scikit-learn, there's conceptual understanding. Are you using the right model? Are you putting the right data in? And are you allowing your model to overfit on the training set? There's so many different things that go into machine learning. And that's why we talk about the theory and the application because they matter in conjunction with each other. And now let's go through like a basic decision tree example for classification to kind of reinforce the stuff that I kind of was talking about earlier. And this is a lot simpler notebook than the one previously. And one thing I want to ask everyone to kind of keep the class going is what is the importance of actually, the interpretable model part I already asked earlier. Okay, so Denny's asked, how do we deal with outliers? Well, there's a lot of different ways you can deal with outliers. One way is you can transform your data. So if you're going to GPT right now and you ask a question like, why do people standardize their or scale their data? This is one way people deal with outliers. By standardize, I mean something like the following. So oftentimes what you can end up doing is you can transform your data such that all your data is within, essentially you can do a couple different things. You can standardize your data, which means you subtract the mean from your training set and divide by the standard deviation so that all your data is roughly on the same scale. You can min-max scale your data. You can do things like that. There's a lot of different techniques and it depends on your use case, but that's kind of another way to deal with the outliers. Additionally, one important thing about outliers that I think you should think about is if you have an outlier that's pretty hilarious, it actually should be removed, most likely. One example I saw in like 5-10 years ago is people had like actual physical machines and they were like sensors on trains, for example. And one thing with sensors is like they had some pretty hilarious outliers. So like people are getting like sensor readings that were like the temperature of the sun. And if that happens, well, that outlier is actually just garbage data. So you probably remove that, but it's also a very good signal that you really should go change that sensor or go see that something's, or go check to see something's going on. Are the sensors around it failing as well? There's something really wrong. Usually those outliers are actually predictive of like something really horrible happening or just a sensor going down. Okay, so let's go through this notebook and see how much we can go through in time. So like usual, we import the libraries we want to use. We're doing a simple iris data set to keep it very relaxed. We're doing our train test split, and all this code is really doing is separating out our data frame into a training set and our testing set. It's worth noting that I'm not really doing much transformation to this data. I haven't scaled it in any way. I'm not doing anything special to it. Decision trees are really nice in the fact that I don't have to standardize my data, like make a given column have a mean of 0 and a standard deviation of 1. I don't have to scale it. There's not a lot of other transformation I need to do. It's really easy just to work with it out of the box. And so one thing I want to ask and like mention here is like for the max depth parameter, max depth is not always equal to depth. I can allow you to grow to a depth of 5. I say like you can totally do that. But if you end up isolating all the classes by the time you get to 4 questions, 1, 2, 3, 4, I allowed it to grow to a depth of 5. But what you notice over here is that I have all pure classes. In this node, all the flowers are versicolor. In this node, all virginica. In this one, all versicolor, et cetera, et cetera. So there's no need to have a 5th question. Like I'm not getting any information gain by just keep on splitting these samples. So in this case, I'm saying max depth equal to 2. And of course, maybe I should set to max depth equal to 3. Maybe that's a better model. And that's why we tune our hyperparameters. And then one thing I'll end up finding is I can go through the same process of having the model learn the relationship between our features and our target, and then make predictions on data hasn't seen before, where the prediction of a 2 here, I believe in this data set, a 0 is, let me see what the classes are. I have to actually look at the documentation. Ooh, it'd be terrible. A 0 is one of the flowers, a 1 is a different flower, and a 2 is a different flower. So that's one really important thing, of course, right? If you have this result from a model and you show your boss, well, if it's a 2, maybe that's a virginica flower. I can't just show the boss, hey, like the class 2 did really well. And the boss asks, like, what is class 2? And I'll be like, I don't know. In this case, I believe it's virginica, but I can be completely wrong. And one thing we ended up finding over here is if you look at the max depth and then accuracy, like how well it does on the train set, well, or sorry, in the testing set, one thing I ended up finding is that max depth of 3 does pretty well. And the thing I want you to get from this is you typically want to have the simplest model that does the best performance. So in this case, what model did I choose? I'd recommend you choose a model that has the hyperparameter value was a max depth of 3, not 4 or 5 here, simply because, first of all, the model might have perfectly isolated classes by max up to 3. And also, even if you did have a model that performed really well and it actually had 4 different questions that lead to a prediction, or 5 even, well, more complicated models are harder to maintain. This is a very simple model that we're covering right now, but it's still a truth that you can kind of take forward to more complicated models. And if you have questions, feel free to ask. We're not in a rush today. It's a lot of content. And the next thing I want to talk about is I want to give a little bit of time to talk about random forests. But let's first talk about visualizing. I don't have time to go through this all entirely right now because I want to talk about random forests. I want to talk about logistic regression and like where to go from here, essentially, from a very basic notebook. So we went over the iris data set, which is very, very simple. And we basically created models that would then lead to predictions. But one thing you could do is you can also visualize decision trees using Matplotlib. And for a lot of you, I think this is a very useful thing. You may not use decision trees in your average day-to-day life, but they're a very common algorithm that a lot of algorithms are based on. So like random forests, which we'll talk about in a second, they're based on decision trees. Gradient boosting methods, they're based on decision trees. And a lot of gradient boosting methods, even these days, can sometimes even outperform LLMs for a lot of different reasons, depending on the use case. So what we find over here is after we fit our model in the data, so after we make an instance for a model, we fit our model in the data, well, we have some sort of visual here, like underneath the hood. This is how the model makes a prediction. So we can make a default visualization based on the model. And one thing you'll find over here is that this is really hard to read. This is a default thing that comes from Scikit-learn. So this tree, if you actually go to the top, this is just a library I imported from Scikit-learn import tree. This is just a visualization aspect of the Scikit-learn library. And I believe underneath the hood actually uses Matplotlib. So we see over here that it's basically telling us if something is less than or equal to 0.8. Depending on that, you go left or right. It's really hard to tell, honestly. And it's a little bit small, so it's not perfect. So you can obviously do little things like you can make a figure and an axis. You can basically make it a little bit bigger so people can see, assuming that's what you want. But like anything, it's often nice to be able to spend some time and make a model more interpretable by putting the features that these x's represent. Again, x's basically are features, and y is our target, basically the values here, the classes. And we want to find over here is that this is a little bit prettier of an image. We say we're a figure, and we can basically have a series of questions that predict essentially what class or basically what flower species these things are. And that works out pretty well. But one thing I want to emphasize here is that this is a very interpretable model, which matters for a lot of applications. You want to be able to explain why a model does a certain thing and why it doesn't do something. That's very important for some applications. However, the next notebook I want to talk about is something I hope that most of you have been a little bit more excited to interact with and talk about. Is this next part is simply about random forests, which are a model which is based on decision trees. So this is something that is a little bit complicated, so I promise we'll go slow. We'll introduce a little bit of theory here, and that's why this particular notebook, in fact, is actually why I call this from theory to application, because there's quite a bit of theory that goes into this, and let's try to make it relatively simple. I also made a video version of this, by the way, in case you want to go through this in a lot of detail. So the one thing I want to talk about first is something called bagging algorithms. And one thing you might notice from decision trees is that, especially from this notebook over here, is that when we have models and we allow them to grow a lot, they tend to perform worse. Well, but this model was able to get some of the trends that maybe this model was not able to get. My point here is like maybe this model maxed up to equal to 5, maybe it got some answers right that this model didn't happen to get right. But maybe this model has some value still. Maybe. Right? Well, there's something called bootstrapping. And essentially, we have bagging algorithms. And random forests and bag trees can be classified as bagging algorithms. And what they essentially are is the first step is you do bootstrap sampling. Well, I know a lot of you are probably not very familiar with bootstrap sampling. So let me just ask, would you apply a clipping or a standardization algorithm to input data? So you can do standardization. Clipping is depending on the use case. Basically improve data training quality, absolutely. You have to standardize data for a lot of things. Absolutely. Why is it harder to maintain mean? I'm not sure about that question. If you want to ask it or you want to clarify a question, I can answer it or try to. But my question for everyone right now is anyone familiar with bootstrap sampling? I'm happy to go over it because I literally made this. Is everyone familiar with bootstrap sampling? Awesome. Okay. Makes 2 of us, 3 of us. Okay. So one important thing about machine learning, yeah, let's take a look at it, right? So basically what ends up happening is decision trees are high variance algorithms. They do pretty well to memorize the training set, but oftentimes they tend to not generalize too well in the testing set. Well, what if you can take the best of all the models, like different decision trees, like how you train them, and basically have them combine to make a prediction? So one way you do this is through a 2-step process where you first bootstrap sample, I'll talk about what that means, and then you average decision tree predictions. Well, if I went through this notebook and I did the same fit step, let's say if I ran this code, let's see, I'm scrolling up 1 second. For this fit step, okay, if I fit the model in the data for the same max depth value, or I let the model grow unconstrained, a max depth of none, I let it have as many questions as it wants. Well, what's one problem I'd have if I let trees grow infinitely big, and if they're all trained the same data? So what is the problem I would have if multiple models of the same model are trained on the same data? You can always take a guess, by the way. Overfitting, that's true. That will happen. But if I'm averaging multiple of the same models together and then aggregating the prediction, what's the problem with this? So if I take the average of 5, 5, and 5, like, okay, let's just do this, like simple math. What's the average prediction? This is easy. Of Setosa, and Setosa? And I had a majority vote. So like this prediction will predict Setosa. This will predict Setosa flower species. Well, that's great. I mean, I can train the same model multiple times, right? Yeah, I can really, yeah, it's the same thing, right? There's no variance and there's no new info. That's very good, everyone. So what people end up doing is they do something called bootstrap sampling. And this is where you create multiple training sets by randomly drawing samples with replacement from the original data set. And the way this works is let's say you have 100 rows of data, you sample the replacement from the original data set until you get to 100 rows. If you do sampling with replacement, it's entirely possible you get the same thing. You can have duplicate rows. So you're not going to get the same 100 rows you originally had because it's sampling with replacement. Well, as far as what that means in real life, well, statistically speaking, and I'll go over the math here in a second, each bootstrap data set contains about 63% of the unique rows from the original data set, and the remaining 36 or 37% are left out and can be used for out-of-bag evaluation. So I obviously don't expect you to know the math off the top of your head. That's not realistic. Same thing with replacement. The way this is you take a marble out of a jar, you record it. You're like, oh yeah, this is this thing. So like I took this out of the jar of my drinks from down below. I recorded it. This is a lemon lime flavored sparkling water. And I put it back into where I keep all my sparkling waters. And then it's likely, if I sample, I'll get some new sparkling water, this red one, and I'll record it and put it back. But it's entirely possible, if I keep on sampling the replacement, that I'll get the same water again, even though they're supposed to be all unique, special sparkling waters or whatever. I used to do some marbles, but I just don't have them on hand today. And then that's sampling with replacement. And then mathematically, what this ends up looking like in Python is you can sample rows from the same data set we had and then get the same row index 8 multiple times. And I can also get some rows not at all. So I can have 3 rows with the index level 8 or however many. It just depends on the random seed. And so what it ends up coming in math-wise is if you actually go through basic statistics, and for a single sample replacement, the probability that a row that is not randomly sampled replacement from the data set it's 1 minus 1 over n, and where n is the number of times you have to sample. And basically you do some archaic like limit calculus kind of stuff. You end up finding that probability is 0.368. It's just limits. If you're curious about this, you're welcome to check it out, but it's not super pertinent for what we're doing. So going back to that notebook, because I think we're running a little bit out of time. So we bootstrap sample n times, where n is how many decision trees you want to come together to make a prediction. So in Scikit-learn, they call this an estimator. It's just a tree in this case. An estimator is just a model, and these bootstrap data sets are all different. In theory, if you do it enough times, it's theoretically possible to get the same bootstrap data set, but it's extremely unlikely. And then so finally, when you have these trees that are trained on different data, for a given sample, if it's a classification problem, they vote, like Setosa. I believe that's Setosa. Kimberly believes that's Virginica. Matthew believes that's Setosa, and we just take the majority vote. And Roshan believes that's Virginica. And assuming we have an odd number, we can have a tie-breaking vote, so to speak. And it's really unlikely you have that problem. For regression problems, by the way, it's still the average prediction. So if Kimberly thinks that's 100,000, I think it's 102. Let's see. Mr. Shi thinks it's 100. Well, we take the average of the prediction, basically. And so you might be wondering, well, what's the difference between a bag tree and a random forest, right? I gave you the same diagram for a bag tree and a random forest algorithm. And most of you probably have never heard of a bag tree. A lot of you probably have heard of random forest because they're more commonly used. Well, as far as what makes a random forest different than a bag tree, so to speak, we were talking about split points for our decision trees. And trees essentially split in the most opportunistic way to be able to train a better model. Essentially, that's what's happening. And for bag trees, at every split, all features are considered as candidates for the split. one thing I mentioned to you earlier is that the split point, the way you split is you consider all the features and all the different split points you possibly could have, which is a lot, and you choose the corresponding feature and the best split point that results in a better trained model, essentially, in a better model. Well, for bagged trees, I allow you to consider all the features. For a random forest, well, it's random. It's in the name. At each split, only a random subset, M features, is selected as candidates from all features P. And the reason why you do this is actually, let me ask you, why would I only want to have a model consider some features and not all of them? I say some features for a given split point. Like a bag tree or a random forest. Does anyone have any thoughts? If I give a question here, like what's the most important feature that determines home prices? Let's say all of you happen to think it's square feet. Yeah, CPU complexity, that's fair. Yeah, features. So I think the best way to explain this is that sometimes you have a really, really, really strong feature, and the model for every split point will just keep on, making questions about square feet or making questions about, is it a waterfront property or not? Well, the problem with that, though, is like the whole point we go through this bootstrap sampling, which is sampling of the placement until we get up to the same size as the original data set. We train individual models. It's like the whole point is we want the models to be different. And it's hopefully the case, but not always. Sometimes you have a feature that's so strong that the models only consider that one feature. And the problem is when you're averaging, the whole point of the random forest is you want to have high variance between your different individual decision trees, as you can see on the screen here. And so one thing you end up doing is for random forest, they select some subset of features from the entire candidate set. And it's randomly selected. The one danger with this, by the way, is if you have features that are garbage, like a feature that's completely random noise, well, a model is only as good as the data it's trained on. So if you have bad features, clean and do some good feature selection, well, you're not going to have a good time. The model actually might perform worse as a random forest, which is a bag tree. In practice, the times when I see people use a true bag tree model versus a random forest is when they have some features that are complete garbage that they don't want the random forest randomly selecting on. So I think this is a little bit more foolproof than this. This often performs much better, but it's pretty hard to have a bad model on this, is what I'm getting at. And so the way this works in practice, because I want to talk about things, is let me see if I can find a visualization for people to understand what this ends up looking like. Let's see if I can find it. One second. I'm looking for a visualization. Okay. So from this same data set, like for 100 estimators, i.e. 100 decision trees, what we end up finding is these are 100 decision trees that are trained on Bootstrap data. And these are the 100 estimators that make up that random forest. One thing you might notice is that these trees, you can't see what's inside of them because it's way too small. What we end up finding is that these trees are all looking a little bit different. And the reason why they look different is that for a given split point, it was only allowed to consider a certain number of features. They all look, a little bit different, so to speak. And of course, you can go through this, but it's all the same thing. Like the trees are allowed to grow as much as they want, because in random forest, you let the trees typically have max depth equal to none. So you let them grow as much as they want, and they take the average prediction of all these different models. And in theory, the what's it called? Groupthink is better than individual think. So this model might have some issues. When you combine this model with all the other ones, it tends to do pretty well. It's kind of what random forest actually ends up being. So I'm going to rush a little bit on this, but to go through the code without having to actually talk about it too much. Well, going back to someone's question about hyperparameter tuning, for the same dataset we had before, and for the same sort of model, we go through the same sort of process, where we make an instance of a random forest model, and estimator is how many trees are coming together to make a prediction. We can set how many features are considered each split. So let's say we have 9 features. At each split, I randomly want to select 3. This thing I'll not talk about. There's no time for this. And then we fit the model in the data, and we can make a prediction, so to speak. And then from here, one thing I want to mention is like a big part of machine learning, as Jake van der Plas kind of talked about, and everyone, is that we tune models, we tune hyperparameters with different techniques. So one way is grid search. And this is where we essentially give a model a parameter grid. We allow it to go through every possible value, which it could be very computationally intensive. We have multiple different hyperparameters, and it'll end up going through every possible combination of its hyperparameters. This is the learning part of machine learning. From here, we do something called the grid search. We're going through every possible value of this. This is just saving us from doing a complex for loop. We put in our estimator, we put it in our instance of our model, which is set up here. We're putting in our hyperparameters. And we're basically saying we want to do 5-fold cross-validation, which is something that was briefly covered at the end of the train test split notebook. We put in our scoring metric. And then one thing we do over here that's a little bit unique is we're setting n jobs equal to -1. And what I'm doing over here is that I told you earlier that my computer has 12 cores. Well, by default, Scikit-learn, often these algorithms run on a single core. And one issue that you might encounter here is like, why might you want an algorithm, especially like a random forest, to run on at more cores than just one? Can anyone tell me why? Why might you want n jobs equal to -1 if you have a machine with multiple cores? This is a bit of an advanced question. If you think about this image on the left here, one thing that's really cool that we could do if we were like a really good team is the process of me creating bootstrap data number 1, like where I'm doing sampling with replacement to create a data set that's the same size as my original. And I'm taking marbles of the bag, and yeah, we're using all the cores for computation. It's really important because in theory, this is a very parallelizable process. Yeah. So it's not auto-tuning algorithm to all. It basically we're giving it all available cores to train the model, and it'll parallelize appropriately. Of course, it's more complex in terms of like parallelization is not always simple. This is a pretty easy algorithm to parallelize. So in theory, Matthew, you could train bootstrap data number 1 on decision tree. Marcel can do bootstrap data number 2. Roshan can do 3. And then at the end, we all combine our model's prediction. It's a very parallelizable process. And of course, you might be limited by Michael if I'm taking longer to bootstrap my data and train my model, in theory. But with my computer, it's pretty much going to finish around the same time because we're doing the same sampling technique. We're doing the same decision tree training. And so when you want to do like a prediction or, for train set, anything, or prediction of the testing set, well, it's going to be a lot faster to parallelize this process because it's a relatively complex model. And so that's why when you're doing n jobs equal to -1, well, in theory, I can do this process. I can set the max depth. I could be running one random forest process with max depth equal to none. Someone else can do random forest, process equal to 5, 10, whatever, depending on how it parallelizes, if it's efficient or not. In theory, it's gonna be a lot faster, right? And of course, different models have different benefits. So random forest, in theory, can tell you which features were very important for prediction based on what we saw earlier. So the features that are most important typically are the first feature it splits on. So in theory, if you take the average of all these trees, what they say the most important feature is, in theory, you can kind of get an idea of like what the most important feature is that comes to prediction. It's not a perfect thing for sure, but I kind of wanted to mention that. And there's different metrics to do it, but the goal in the end of like today that I wanted to get you from this presentation is that machine learning is really a process where we want the model to learn some relationship between our features and our target for supervised learning. I didn't get to unsupervised learning in this process, but there's algorithms that can help you understand your data by essentially data compression, where we go from a high dimensional space, like in the iris data set, to a lower dimensional space. But that's really what I want to cover today. If you have questions, please feel free to let me know. I'll be online as much as they allow me to. And yeah, I didn't get to cover everything, but I hope everyone learned a lot. And yeah, let's take questions. It's better to have a lot of questions going through and then trying to force going through 10,000 different things. So if you have questions, you can ask me right now. You can also add me on LinkedIn. You can add each other on LinkedIn. There's a lot of different ways to reach each other. Where do you see bridge gaps between machine learning using supervised learning, unsupervised, and then reinforcement learning? When do you start using reinforcement learning plus unsupervised and then augment that and improve by using RL? So it really depends on the problem at hand. One issue that I happen to see a lot in real life is that we tend to go very complex before testing out baselines. And even in research, one thing that we ended up finding is that, for us to, because I'm a grad student now, for some reason I decided to go back to school, which is another story entirely. And the one thing is are you getting good results with your supervised learning? That's one thing. If you don't have a target and you're using some sort of clustering algorithm to segment your customers, if that's enough, then we don't need to do something more complicated than what we currently have. For reinforcement learning, there's often cases where, let me actually share my screen again. So what we end up finding is there's some cases where the problem at hand is just not going to work. You see this for simple things like cart pull, where you're trying to teach, some actuator to kind of stand up on its own. You kind of have to give it some sort of feedback to kind of improve a process. And this doesn't tend to work too well at first. But if you give a model some sort of reward, well, maybe it's going to learn something a different way. And that's the way people often use to train games, is through reinforcement learning, because it's a model interacting in some environment via trial and error. And there's some sort of feedback loop that's very, very apparent. So you have some sort of policy, some agent basically does some action, interacts with some environment. And this is traditional reinforcement learning, really simple stuff. You have some sort of reward. If it does something good, you reward it. And then the model keeps on improving, right? And that's a really simple type of reinforcement learning. The problem that we see today, where we want to use supervised and then augment that with reinforcement learning, and I keep on going to this paper because I'm actually doing a paper based on this. So like, please don't hate me for this because it's not a simple paper. Is like, there's some cases where, let's say we have some sort of documents and we have some sort of reasoning on those documents. We want to teach a model how to be better as a reasoner in today's world. Because a lot of problems right now are like, can you reason through a math problem? Can you improve this code to be more logical? Can you improve this code to be better? Well, you start off by giving something examples of like some sort of features, and then you have some sort of target, which is some sort of reasoning. Well, at some point, that's really a pretty unsupervised process. Well, you could do a lot of different ways, but eventually you end up going to like some sort of reinforced fine tuning where you have some sort of documents, you have some sort of reasoning, and based on if an LM generates something that you want, you get some sort of reward, and you have the model improve that way. Because oftentimes for a lot of LM training right now, it's basically just showing a lot of information and not really giving too much feedback on the information. That's when you go into the reinforcement learning, basically. There's also reinforcement learning for human feedback and pre models to understand humans and stuff like that. That's also when you do the RL. And to be honest with you, I'm not an expert in RL either. I know one person that is, and they are paid extraordinarily well. So can you talk briefly about the process of data collection deployment and what are the most important steps? So one important part about data collection and deployment is essentially, how should I say this? Evidently, AI. Okay. One really important thing about data collection is, first of all, is your data representative of the world around it? So are you able to get a good sample of data? That's probably the most important part. If your sample is biased, well, your model's gonna be biased in some way. So you get the data, you collect it, make sure it's good, make sure you're allowed to use it for your use case. Because if you can't use the data for your production use case, you might get sued, you might get in trouble. But the other issue you might have that's kind of important to talk about, let me see if I can find something. I'm trying to find a nice diagram here. Okay. So one issue you might have is that sometimes when you gather the data, the world is so much different than the model that you release in the wild. So sometimes you have to really like update your model over time. So ML deployment, and I'm using my old criteria because at least I know where things are. Not that I'm good or anything about all this stuff. I just happen to know where the content is. So one really big important part is, please say this is actually what I'm looking for. Okay, I can't find it. But if models are only good for so long, are you able to keep on updating your model over time quick enough where the deployment is actually useful still? So it's not just train a model, make sure it's good sample, and then deploying it in an efficient way that you're not wasting a lot of money. But it's also, are you able to keep on updating the data and retrain the model fast enough that the model still performs well? Because one issue I often find people have is they might have a really good model initially, but their retraining process is too slow, that they're often better off having a simpler model and then retraining it more often and re-updating the model in production because the data changes so quickly. It's a very important thing. And then the question about curriculum learning, not quite. So curriculum learning is like, as you probably know even better than me maybe, curriculum learning is when you start with something really simple and you have a model learn something simple because it needs to learn something more complex over time, right? So you start with like, ABCs before you get to understanding stories, and then, so on and so forth. Like there are some like hierarchical papers these days. AI, I'm not sure this is the one I'm thinking of, but these days there's some skills that models need to learn that are very much like you learn one skill before you can learn another, before you can learn another. Models tend to train better that way. And that's kind of a curriculum type of learning. There's like almost a hierarchy of skills you need to learn. And that's supposed to train a model faster. Supposed to. It's not easy to do.
Thank you everyone for joining again, and thank you, Michael, for this really interactive and interesting session. I'm sharing a feedback form, so if you want to leave a feedback and help us to improve future conferences, please leave your feedback. I see one more question popping, so.
I can answer it if you want. Okay. And thank you so much, by the way. So what about feature engineering? How do you improve features so you learn more about a data set? Well, that's a hard part. I gave you I quoted the easy part about the machine learning today, like especially the simpler models. Well, for feature engineering, a big part of it depends on your use case. So one thing people actually do that I didn't cover at all, there are some machine learning algorithms people use, like a random forest. For example, they actually do use a random forest, or like a logistic regression, which didn't have time to cover, with a strong L1 penalty. And the features that don't go to 0 for logistic regression, they actually use those as the features to get rid of some columns that are too hard to maintain. And there's also something called the curse of dimensionality, where if you have too many features, models actually perform worse. So like maintaining features is like a big thing, and about having minimum features to actually maintain. So like one thing you often find is like, I'm not sure this company exists anymore, but people often have ways to update features and then monitor the features that they don't like change too much over time. So that's actually like one really important thing. For the stuff we did today, like even doing simple things like creating a feature about when the home was renovated is actually a really important thing. And you just basically see what features perform the best initially. And then which ones you maintain is another story, because maintaining data is very painful. So is that where you apply some sort of feature gating in the model architecture? So I think one thing we often do is we make like things complex, like throwing in feature gates and like maintaining a lot of features. But honestly, one thing I kind of recommend is stick simple. Like make sure your features aren't correlated. Use a machine learning model to select one feature, and then use a different model to actually train on the data. Like keep it really simple. I say, use a model to select features. It's actually sometimes simpler than maintaining that many features.